actually transporting the media, we don't use TCP, we use UDP. TCP does retransmits, UDP doesn't. And UDP provides us with a best efforts communication service over an IP network. So this is used to transport the actual media. And when we're talking about voice over IP, the media would be coded using one of the codecs, which we're going to look at next, and then it gets time-stamped using RTP, and then that goes into a UDP protocol data unit, and then that goes into an IP packet to be transported across the IP network. And at the far end, we pull in the IP packet, pull the stuff out of there and give it to the UDP, pull the stuff out of that and give it to the RTP, and we use the RTP information to try to fix timing variations and lost packets. And we're going to go through all of that stuff in the next discussion. Interestingly, not all of the signaling happens over a TCP connection. The H.225 registration, admission, and status functions happen over UDP, whereas the H.225 Q.931 call setup functions happen over TCP. And also SIP happens over UDP as well. SIP is a competing strategy for doing call setup, competing with H.225. Talking about cost effectiveness and ease of integration in call centers and fancy new features is fine, but it's voice quality that is going to end up being the determining factor as to whether a voice over IP implementation is successful or not. If it doesn't sound good to the user at the far end of a conversation, it's going to be a big problem. When we start looking at what causes voice to sound good or not, what we find is that there are a number of different components. One of them is the compression method, and we're going to take a look at the different codecs that can be used in voice over IP and whether they are variable rate codecs or not. Another obvious factor would be the bandwidth, and what we mean by bandwidth is capacity measured in bits per second. And of course, how often those bits per second happen and how often they don't happen would be another question. So we could think that somebody with a 56K dial-up connection to the internet is probably going to end up reproduced sound at the far end that isn't as good as somebody with a cable modem or a DSL connection or a 10 megabit per second Ethernet connection. Perhaps the most important factor is delay. And there are a couple of aspects to this. One of them is the total end-to-end delay. And not just because of the delays getting so extreme that you end up having to go into a half-duplex mode of communications where first you talk and then you have to wait and the other person talks, even though in theory the communications is both way at the same time. We see this on CNN with television reporters when they're going across several links or hops of geosynchronous satellites. The delay is so long that they can't have an easy conversation really in real time. But besides that, and hopefully we would never get to those extremes, the maximum end-to-end delay is limited because if we exceed it, then we start hearing echoes. And we're going to talk about that, of course, as we go through this chapter in more detail. Now, besides the question of delay, there's actually a second order problem which is more important, and that's variability in delay, and this is referred to as jitter. Another thing that causes us to have bad quality reconstructed speech at the far end is losing chunks of data, losing packets. So we're going to be interested in discussing what happens when we lose packets, what does it sound like, what would be the maximum specification for that, and how could we possibly recover from lost packets. Delay, variability in delay, and packet loss all end up being related to network loading. And as we go through this chapter, we're going to see what exactly I mean by network loading and the actual mechanism that causes variable delay and packet loss. The solution to all of this ends up being good network design. And what we have to do is either design the wide area network with unlimited capacity, so there are no problems with packet loss or congestion or anything like that, or if we end up with a situation where there is contention for communication of IP packets, and whether this is contention between multiple people's phone calls or contention between voice packets and data packets, we're going to have to try to figure out how to implement some sort of quality of service guarantees across the network in order to make the reconstructed speech sound good. Now, when we're measuring quality of speech, it isn't obvious how you could design a computer program to make objective measurements like signal to noise ratio and packet loss and things like that, and directly correlate them with what a person would think it sounds like. When we're talking about analyzing the quality of speech and video for that matter, we usually end up doing subjective testing. And what we do is we get people in shopping malls and pay them $10 to come into a room and look at some impaired video or listen to some speech and rate it on a scale. And if we want to get really academic about this, we give them a scale from 1 to 5, and we might tell them which end is which, like 1 is good and 5 is bad, although sometimes we don't even do that. But we don't really tell them what the individual levels mean. Like, we don't say that 1 means really good and 2 means okay and so forth. We let them figure that out for themselves. And the idea is that if you get enough subjects in who rate things on a scale of 1 to 5, then by definition the result is that we end up with what our society thinks is a scale to 1 to 5. And of course you need to get quite a few people in order to do that. Now, if we don't have that many people, then we might use some historical sort of scale of 1 to 5 that has been developed by lots of other people doing subjective testing of what we're interested in. And in voice communications, this is called the mean opinion score. And it's a scale of 1 to 5, 5 being the best and 1 being the worst. If you look at this chart, you'll see that the mean opinion score for voice communications is that a score of 5 means that it's excellent, and a score of 4 is good, a score of 3 is fair, 2 is poor, and 1 is bad. And it has a listening effort scale column where excellent means that complete relaxation is possible and no effort is required. Good means that you have to pay attention but no appreciable effort is required. Fair means that you have to pay attention, you need some effort in order to understand. Poor, meaning that considerable effort is required in order to understand. And bad means that no meaning is understood with any reasonable amount of effort. Now, I think of this as if you were learning a second language as an adult. Before you start learning the language, if you watched a television program or a movie in this language, it would just be gibberish. You wouldn't understand anything. And then as you started learning some words in the language, you could start getting some meaning out of this flow of noise that's coming to you, but essentially what you're doing is table lookups on each individual word. So this is a considerable effort. That would be a scale of 2. And then once you realize that people talk in phrases and you start learning these phrases and the ones that are used in the particular society that you're interested in, then you can start getting a bit more information going back and forth, but you need quite a bit of effort still. This would be a scale of 3. And then once you become proficient at the language, you might actually be able to go to the cinema and watch a movie in this other language, but you're going to have to pay attention. If you don't pay attention, you're not going to understand. And for most of us, when you learn a second language as an adult, you would never get to level 5. You wouldn't be able to